Okay, so now we're going to first recap isotopes and your understanding of them, and then introduce the periodic table and some other chemistry terminology that you need to know and understand. So first, we've already defined isotopes, but again, they're atoms which have the same atomic number but different atomic masses because they have different numbers of neutrons. And that atomic number, or zeta, designated by that capital Z, is the number of protons found in the nucleus. And that number is also on the periodic table. So you can always identify the number of protons by the atomic number found on the periodic table. The mass number, designated by the capital letter A, on the other hand, is the sum of the protons and the neutrons in that nucleus. And so you can determine, never mind, I was a step ahead here. We can use that mass number and the atomic number to determine the number of neutrons if we're asked to do so. Okay? So here we're looking at a generic representation of the isotopic symbol, where X is an element symbol. The superscript A is the mass number, and the subscript Z, or zeta, is the atomic number. And you'll see the three forms of hydrogen isotopes given in that designation. There is another way to do this, and I'll show you that, and then I want to come back and talk more about the hydrogen isotopes. We could also just use the isotopic symbol, a dash, and the mass number. So that's another way to represent an isotope. So in other words, we could write the isotopic symbol for protium, which is what this is called, and it is the most abundant isotope of hydrogen. And if I were to ask you how many protons are present in protium, you would look at the atomic number, which is here. So there's one proton. And in fact, all of these isotopes have the same number of protons. Not surprising, because the number of protons doesn't change, but the number of neutrons does. And in protium, there are 0 neutrons, because that mass number is 1. Deuterium, on the other hand, is also a stable isotope. It's naturally occurring, and it's abundantly found in oceans. It has 1 neutron. Mass number -1, the atomic number, gives us the number of neutrons. And for tritium, which is a radioactive isotope of hydrogen, it has a half-life of 12 years, so it doesn't decay very rapidly. It has, of course, 1 proton, and it has 2 neutrons. So, in order to determine the number of neutrons, we're just subtracting the atomic number from the mass number, and we get 2 neutrons. So we could also represent deuterium with an H-2 and tritium with an H-3. So just do you get it kind of slide here? How many protons, neutrons, and electrons are in this isotope of carbon, or carbon-14? Again, we could write that as C14. Remember, protons are always constant, and in an electrically neutral atom, that means there are no charges, electrons will equal protons. Again, our number of protons is given by the atomic number, and the number of neutrons is determined by subtracting 6, or the atomic number, from the mass number. So our number of neutrons then is going to be 8. I think that's right here. Now this one, another isotope of carbon, C11. And again, protons remain constant. This is a neutral atom, so protons equal electrons. Protons equal electrons. And there are then 6 protons and 6 electrons. And the number of neutrons, again, will be determined by subtracting 6 from 11. So we have 5 neutrons. So let's take a look at the periodic table. It is one of the most valuable pieces of reference material that you will ever work with in chemistry. Trust me, so much information here. Basically, the elements are arranged in order of increasing atomic number, and you see start with atomic number 1 here for hydrogen, and we jump over to helium, and then in the next row we have 3, 4, and then we go from 5 to 10 here. So when we read this, we really just go row by row down the periodic table, okay? So these rows are called periods, okay? So when moving left to right across the periodic table, we are going across a period. If we go down a column or a group, these elements are all going to be in the same family. Some of these families have names, and you are going to be responsible for that name. Another aspect of the elements in a group or a family is that they have the same number of valence electrons, thus they have the same electron configuration in their outermost energy level. And because they have the same number of valence electrons, they have similar chemical properties. They behave similarly. Now you'll also notice at the headings of these families, we have 1A, 2A, we jump over here, 3A up to 8A. These are the main group elements or the representative elements. They have follow common characteristics and rules. You'll notice that there are these B's, 3B, 4B, 5B. While these are all metals in this family, they do behave differently than the main group metals, and we'll talk about that more later. What else did I want to say here? Let's just say, well, let's classify the metals here. You'll notice the metals are represented in green. Groups 1A, 2A, and 3A are those main group or representative metals. The blue highlighted elements are nonmetals, and you can see in comparison most of the elements in this periodic table are metals. And then we have this very other smaller group that follows this zigzag line down at a diagonal. These are the metalloids, and the metalloids are going to have properties of both metals and nonmetals, depending upon what their identity is. So I said that some of these families have names that you need to know. The first family in group 1A are the alkali metals. These metals all have one valence electron. They are highly reactive. In fact, many of them are not found by themselves in nature. They're so reactive that they don't exist as individual metal atoms when exposed to other elements. Group 2A are the alkali earth metals. These have two valence electrons. So I should have noted this as well, that for the main group metals that is, the Roman numeral or the number at the top of the column tells us how many valence electrons there are, which will be meaningful later. So group 2A has 2 valence electrons, and main group 3A has 3 valence electrons. 4 valence electrons, 5, 6, 7, 8 valence electrons. So you can get the number of valence electrons by that number at the head of that main group column. So this block here that's represented by that letter B, this block is called the transition metal region. These metals, while they have the same number of valence electrons, for example, in a family, they don't form predictably charged ions like our main group metals do. And we'll talk about that more when we introduce the nomenclature or the naming of ionic compounds and covalent compounds. Of course, down here we have the lanthanides and actinides. When we start writing electron configurations, we will label what we're going to call blocks in the periodic table, and I won't go there yet, but that will be coming up at some point. I did mention, oh, I'm sorry, not done with families. Group 7A, halogens. And then, of course, in Group 8A, the noble gases. So you are responsible for the terms, period, group, understand what they mean, and what's happening. So if we're moving from left to right across this periodic table, we're adding protons and electrons. 1 proton, 1 electron as we move from left to right. And I think that's it for this slide. Yep. So again, more terminology. Molecule or a molecule is a group of 2 or more atoms in a defined arrangement held together by chemical forces. So what that means is that these are covalent molecules. They are molecules that have atoms that are sharing electrons, different from ionic compounds, which are held together by ionic bonds, not chemical bonds, or an electrostatic attraction. So Here we go. Examples. H2. So there are a number of elements that exist as diatomic molecules. Okay. They may be homodiatomic, which is the case of H2. So all that means is it's two hydrogen atoms bonded together, but other elements that exist naturally in this form are hydrogen, H2, N2, O2, F2, Cl2, Br2, and I2. And we'll talk about a rule that allows us to identify which elements behave that way. So this is a diatomic molecule. These are just, regular, no special name for these based on the number. But water, we've got one atom of oxygen, two hydrogens. In ammonia, we've got one nitrogen, three oxygens. And in methane, we have a carbon bonded to four hydrogens as well. So diatomic molecules contain only two atoms. And as I mentioned, these would be homodiatomic, H2, N2, O2, Br2, but these are also diatomic molecules. Only two atoms bonded together. This is hydrochloric acid, and here this one is carbon monoxide. We can also classify molecules that have more than two atoms in them as polyatomic molecules. So they have more than two atoms. Do not confuse this with polyatomic ions. These are molecules. They are chemically bonded together. They do not carry a charge as a unit. Ozone is an example. Water. So we have three atoms here. Ammonia and methane. So we can more distinctly or more aptly characterize these molecules using, well, not this one, but these three, by using the word polyatomic. All right. So ions are formed by atoms or a group of atoms that have a net positive or negative charge. Okay. So a cation specifically describes an ion with a positive charge. And if a neutral atom loses one or more electrons, it becomes a cation. So here we have a sodium atom. Its atomic number on the periodic table is 11. So the neutral atom contains 11 protons and 11 neutrons. So 11 pluses, 11 minuses. So it has 0 net charge. However, the sodium ion has lost an electron. And when ions form, or the cations form, it's the valence electrons that are lost. Sodium is in group 1A, so it has one valence electron, which will be lost to form the sodium ion. So that means that all of the elements in group 1A have one valence electron, and will lose that one valence electron to form a +1 cation. So we can also use that number at the head of that family or group to tell us, for the metals, main group metals, 1A, 2, and 3A, the charge of that cation. An anion, on the other hand, is an ion with a negative charge. If a neutral atom gains one or more electrons, it becomes negatively charged because now it has more electrons than protons, and becomes an anion. Chlorine is the example used here. The chlorine atom, atomic number 17 on the periodic table, has 17 protons and 17 electrons. However, the chlorine atom is one electron away of having a full outer shell, or 8 electrons in its outermost shell. So it will gain 1 electron. And we'll talk more about why that happens later. So now it has 17 protons. Remember, proton numbers never, ever, ever change. And it has gained an electron, so it has 18 electrons, thus the -1 charge. And all the elements in group 7A are going to form -1 anions. Some more, another terminology. So monatomic ion means there's only one atom present. So it's just the ion of a particular element. Sodium ion, chloride ion, calcium ion. Take note, calcium is in group 2A, 2 valence electrons. It forms a 2+ cation. Aluminum, group 3A, 3 valence electrons. It forms a 3+ cation. We'll come back to the negatives when we talk more about ion formation. Now, polyatomic ions are a group of nonmetal atoms that are covalently bonded together, so they're sharing electrons, but they have picked up an extra electron or so along the way, or lost, because you'll see there's one here that is positive. And there is a group of polyatomic ions that you will need to know the formula, the name, and the charge for. Don't think I'll list those here because I don't have as much control with this pen. I'll wait till I'm using my laptop. But anyway, some examples: hydroxide ion. This is the cyanide ion, ammonium ion, and the nitrate ion. You're going to learn quite a few number of other names of polyatomic ions. Oh, well, this is out of place. That should have appeared right after our first introduction to the periodic table, but we'll just take a step back here. And actually that's good, because then I can address the charges on the anions over here. Excuse me. So I also had already addressed these just when we were talking about ion formation, but again, group 1A, +1 ions, group 2A, +2 ions, group 3A, +3 ions. You'll notice here in this transition metal block, I said they behave differently, and this is an example of that different behavior. So look at chromium. It can form a 2+ and a 3+. And these aren't all of the possible charges that can form either. Just some examples. Manganese, 2+, 3+. It can also make a 4 and a 7+ ion. Iron, 2+ and 3+, and so forth. So when it comes to naming ionic compounds that contain a transition metal, we have to indicate the charge on that metal. And we'll learn how to do that. So coming back over here to the nonmetals and the anions that they form, you'll notice that the halogens all form -1 anions. Group 6A, -2, 5A, -3, and 4A, -4. You can either memorize that, or the other trick is you take the group numbers, for example, 7A, and subtract 8. And that gives you a -1. 6 minus 8, -2. 5 minus 8, -3. 4 minus 8, -4. So this is where that 8 is coming from. Okay, so this is just to familiarize you with the number of ways that we represent molecules or formulas, and some models that give us a little more information than just the simple molecular formula. So the molecular formula tells us how many of each type of element are present in that molecule. But that's about all it tells us. It doesn't tell us anything about their bonding or how they're attached to one another. So in order to show that, we can use something called a structural formula. So this indicates where the electrons are being shared between the atoms. So we see how they're bonded together. But that still limits the information or our understanding of about how those bonded atoms are arranged in space. So to show or reflect their how they occupy three-dimensional space, we can use ball and stick models. And well, this doesn't seem to show anything more than this representation. I think you can see that for the next few molecules, which are have more atoms in them, you can actually start seeing a shape develop. So this looks like this is a flat linear structure, when in fact it is actually bent. And this looks like a triangle, and well, yeah, there is a triangle down here. This sits up on top of it. So these are not 120-degree bond angles here. Okay. And while this too, the structural formula for methane looks flat, we see that it has, there's such like a triangle here, and then we have our central atom and this atom up here. So the ball and stick model allows us to visualize the three-dimensional shape of that molecule. Space-filling model, on the other hand, gives us an idea of how much space each atom occupies in that molecule. And you'll see for water here, we can see it's a little larger, right? But this gives us a better idea of the amount of space that's occupied by that oxygen atom, as well as the nitrogen and the carbon atoms here. All right, the molecular formula, which we've just seen a moment ago, again shows the exact number of atoms of each element in the smallest unit of that substance. Okay. An empirical formula shows the simplest whole number ratio of atoms in a substance. So the molecular formula is the true formula for a compound, but the empirical formula shows the smallest whole number ratio of atoms in a substance. For example, water, H2O. That is, so sometimes the molecular formula and the empirical formula are going to be the same thing, because we cannot divide this further and get a smaller whole number ratio. For water, the molecular and the empirical formulas are the same. Glucose, on the other hand, has subscripts that are divisible by 6. So the molecular formula, for glucose is C6H12O6, but its empirical formula is CH2O. O3, ozone. 3 is divisible by 3, so the empirical formula is simply O. I don't know if there's another one. One more. Yep. N2H4. Here we have 2 subscripts as well that are divisible by 2. So the empirical formula for that compound is NH2. We're going to be learning how to determine empirical formulas based on laboratory analysis of the composition of compounds, and that will also then allow us to determine the molecular formula, assuming we have the molecular mass of that compound.